So, worksheets 15 through 22 are due on the 30th. Homework number 3 is also due on the 30th. We're coming up on the midterm, it's technically tomorrow, so you need to meet the active pursuit standard. By the midterm, the end of the week, you need to have taken all tests and completed at least half of the assignments, homework, worksheets, etc. And sign on the shine sheet. So continuing off, why are you not working? Where you left off, we were talking about stellar mass. So since mass is the most important factor in understanding a star's life cycle, it's important to be able to measure. Luckily, most stars are in binary pairs, so we can use measurement of their orbital motion to determine their masses. And for those that aren't, it turns out that there are other indicators. So if you have a binary pair of stars, there are 3 ways that they can occur. You can have an orbital binary where you can see both stars. Thus, you can measure their orbits directly. This is the easiest to measure and analyze. Then you can have a spectroscopic binary where you can't see both stars, but you can see the spectral lines of each star. And while one star is moving towards you, it will be blue shifted. While the other star is moving away from you, it will be red shifted. And then lastly, there are eclipsing binaries where one star passes in front of the other. And you can measure variations in the intensity of the light coming from the star. So how do we measure the stellar masses? Well, we use Kepler's third law. If we have a star that's a visual binary where we can see both, we can just see both stars, measure their orbits, use Kepler's third law. A spectroscopic binary, we can separate the 2 stars spectroscopically. We can get their velocities and their periods. That's enough to figure out their masses. And for an eclipsing binary, it's a little trickier, but you can get similar information. So the orbit of a binary spiral system depends only on the strength of the gravity, between the stars. The 3 types, for a visual binary, we can directly observe the orbits because we can see both stars. For a spectroscopic binary, we can observe both. We can observe the velocities from the red shift to blue shift. We can measure those, and as they change, we can work out the period as well. So when on one side of the orbit, star B is approaching us, so its spectrum is blue shifted, while on the other side it's red shifted. This gives us its speed and its period, because you can measure this shift over time, and then you can determine the orbit. For an eclipsing binary, you have the one star moving in front of the other, causing it to dim, and then the other star moving in front of it, causing it to dim. And you get some information of the size, the relative size of the stars. So here, we see light from both A and B. We see light from all of A and some of B, both A and B, and only from A. So Kepler's third law tells us that the semi-major axis cubed is equal to the mass of the 2 stars added together plus the period of the stars. So if you can determine the semi-major axis and the period of the orbit, we can measure the mass of the system. And if you can observe at least something about the individual movement of the stars, you can actually determine the individual masses of the stars. You can figure out like their relative velocities or their relative semi-major axes. So we can measure mass using gravity. So this is the formula with, period squared equals 4 pi squared over big G, the universal constant, mass 1 plus mass 2 times A cubed. And this direct mass measurements are only possible for stars in binary star systems. Something needs to be orbiting to make these measurements. So we need 2 out of 3 observables to measure mass. We need period, orbital separation, A or radius, and orbital velocity. And because for circular orbits, velocity is 2 pi radius over period, you can actually get, if you have velocity and radius, you can get, well, if you have period and velocity, you can get radius, and sort of, if you have period and radius, you can get velocity. If you have any 2, you can get the third. The easiest to measure is period, and then you're going to either get separation or velocity via some method. The most massive stars are about 100 times the mass of the sun, and the least massive stars are about 8% of the mass of the sun. The largest stars are limited to about 120 solar masses. Above 120 solar, so the biggest we've seen are about 100-ish. But a theoretical maximum for normal stars, modern stars, is that 120 solar masses. Because above that, radiation pressure will cause the outer layers to get blown off, basically. And radiation pressure, so that's the point where radiation pressure, the pressure of the light pushing outwards, will actually exceed gravitational force. The theoretical upper limit is for a star that has no metals, so it is minimally dense, and basically heavier elements interfere with this, make it easier for radiation pressure to push off material. So the theoretical upper limit is 300 solar masses. The lowest mass stars are about 1/12 of a solar mass, and the reason that's the minimum is just below that you can't fuse hydrogen into helium. We see things below that, but those are brown dwarfs. And in general, when we look at stars, we can only see points of light, even through the largest telescopes. So there's a few ways to determine diameter. When a moon passes in front of a star, how it dims can be used to figure out the diameter, because there's sort of a process of it dimming as more of it gets cut off by the moon, and the period of time over which that happens, you can work out the diameter. For eclipsing binary stars, these periods of eclipse give you information about the diameters of the stars. And the most common way that's used is the radiation law. The luminosity of the star is equal to 4 pi times the radius squared times sigma, which is a constant, times temperature to the 4th. So as you get hotter stars put out more light, bigger stars put out more light. So if you know the temperature and the luminosity, you can figure out the radius. And diameters range in size. So the smallest stars are around the same size as Jupiter. These are the most common and least massive stars, while the largest stars are much larger than the sun. So giant stars are 10 to 100 times larger than the sun. Supergiant stars are more than 100 times larger than the sun. And the largest known star is DY Canis Majoris, is 1,400 times larger than the sun. This would extend out beyond Jupiter if you put it in our solar system where the sun is located. Mass is the main determiner of properties of stars while they're on the main sequence. So 0.2 solar mass stars down here, 1 solar mass is here, 5 solar masses is here, 15 is up here. If you got more, it would be up here. If you had less, well, you can't get much less, but it would be down here. And there are a lot more small stars down here than there are large ones. There's a lot more small stars than large stars. And this has to do with a couple of factors. One, small stars stick around long. They live long. And two, it seems like in star formation, when clouds of gas break up, you tend to get more smaller lumps that form smaller stars. But in general, there are just a lot more small stars than large ones. And even if you look in a young cluster, there are more small stars than large stars. So stars have a wide variety of masses and diameters, from something akin to the size of Jupiter to something 1,400 times the size of the sun. And there are various methods used to determine the size and mass of a star, mostly looking at binary stars for mass, and then looking at the brightness for size. Large stars in size and mass are more commonly seen in the sky, but small stars, both size and mass, are more common in the universe. They're just dim, so we don't see them as easily. Because we have this selection bias, where we see the big bright stars, we don't notice the more common dimmer stars. So here's a short video about types of star clusters. So stars come in clusters. This is because they tend to be formed. Star formation tends to happen in groups. So clusters of stars tend to form together from the starting material, which was a big cloud of gas and dust. And thus you get.
Before we continue, answer this question. Based on what you have learned about the main sequence, which of these two star clusters contain the most massive main sequence stars? Is it the one on the left, called the Pleiades, with its luminous blue stars, or the one on the right, called M80, in which the most luminous stars are red? The answer is A, the Pleiades, because its most luminous stars are blue, and luminous blue stars are the most massive ones on the main sequence. In fact, the luminous red stars in M80 are giants, which means they are stars that already left the main sequence and are near the ends of their lives. This answer leads us to some important insights into star clusters, which come in two general types. The Pleiades are an example of what we call an open cluster. Open clusters are found in the disk of the galaxy and tend to be young in age. That is why they still contain their short-lived, massive blue stars. M80 is an example of a globular cluster. Most globular clusters are found in the halo of the galaxy and contain only very old stars. We know the ages of these star clusters because of the relationships we have found among the properties of stars. When we plot the HR diagram for an open cluster like the Pleiades, we find that it still contains relatively short-lived stars, much more massive than our Sun. This tells us that it must be much younger than our Sun. In contrast, globular clusters contain only relatively low-mass main sequence stars. This tells us that they must be old enough for their more massive stars to have all died off. In general, precise study of a cluster's main sequence turn-off point allows us to make a fairly precise estimate of its age. To recap, in this video, we have identified the information needed to measure the luminosity, surface temperature, and mass of a star, described the patterns observed among the properties of stars, and identified the two types of star clusters and how we learn their ages. I hope this will help prepare you for.
So, stars come in two types of clusters. These are the two common types. There are open clusters, which are smaller. They have a few thousand loosely packed stars. They tend to have younger, brighter stars in them. They also tend to be in the disk of the galaxy, where there's more active star formation going on. Globular clusters are much bigger. There are a million or more stars in a dense ball bound together by gravity. They tend to be significantly older, and they tend to be in the halo of the galaxy. So there's sort of a sphere of these globular clusters around the galaxy. So there was a period where we had these big globular clusters forming early in the history of the galaxy, and then later star formation moved to the disk, and we got more of these smaller open clusters. And we can date various clusters of stars. So these are the two main types of clusters. And how do we measure the age of a star cluster? Well, we look at all the. So it turns out, if we look at a star cluster, and with our understanding of how stars are born from clouds of gas and dust, well, what's likely to occur is that some whole area got dense enough to start collapsing, and it fragmented into pieces, and each piece became a star. So if we look at a star cluster, all the stars in that star cluster should be about the same age. And that means if we look at a star cluster, we can look at which stars are still on the main sequence and which have moved off the main sequence towards dying. And that can tell us about the lifetime of the star cluster. So you can see each of these star clusters has a turnoff on the main sequence. There's sort of a maximum size above which we don't see stars of that age. H plus chi Persei turns off here. The Pleiades, so it's about 14 million years old. The Pleiades turns off here, so it's about 100 million years old. The Hyades turns off here, so it's about 650 million years old. And NGC 188 turns off here, so it's about 7 billion years old. So what we find is that massive blue stars will die off first, followed by white, yellow, orange, and then red stars. So the Pleiades, for example, has no stars with a life expectancy less than about 100 million years, because we see this turnoff where the stars are leaving the main sequence. That tells us that the Pleiades is about 100 million years old, because all the stars that would have lived less than that have died. And by looking at the main sequence turnoff point for a cluster, we can figure out its age. So this is these several clusters. Here we have Persei. It's a very young cluster because its turnoff is only up here at around 14 million years. The Pleiades is at about 100 million years here. The Hyades is at 650 million years, about here. And NGC 188 is about 7 billion years here. So detailed modeling of the very oldest globular clusters we can identify reveals that they're about 13 billion years old. That gives us sort of a lower limit on the age of the universe. And our understanding from other methods of figuring out the universe is about 13.6, 13.7 billion years old. So by looking at the oldest globular clusters, we can get an idea about how long it took for stars to start forming, basically. So the distances, so in the summary of the chapter, distances to the nearest stars can be measured via parallax. Beyond that, there's a whole ladder of techniques we can use for distance. The most common is something called the standard candle, where there's something where you know precisely how bright it is from some properties. And then by looking at its apparent brightness from Earth, you can figure out its density. I mean, its distance. I don't know why I said density. Apparent brightness is as observed from Earth. It depends on distance and absolute luminosity. So if you know the absolute luminosity and the apparent brightness, you can work out the distance. So there are certain things that we know their absolute luminosity because they're all functionally identical to each other. Certain types of stars, they have properties that correspond with their luminosity. Certain types of events all have known luminosities. We'll talk about them a bit later, because they come up more when we're trying to find things in other galaxies. Spectral classes correspond to different surface temperatures. Stellar size is related to luminosity and temperature. An HR diagram is a plot of luminosity versus temperature, and most stars lie on what is known as the main sequence. So starting with spectroscopic parallax, we can build a distance ladder to extend out to further distances. The masses of stars in binary systems can be measured, and mass determines where a star lies on the main sequence. So that was the end of chapter 17 and 18, and now we're going to move on to 20 and 21 on the interstellar medium and the birth of stars. So the interstellar medium is the stuff in between stars. So when we look at the stuff in between stars, the other material in the galaxy other than stars, which are easy to see. So any material found between the stars, 99% of interstellar material is just gas, interstellar gas, hydrogen and helium floating around in space. There's also interstellar dust, where these are like tiny soot-like or sand-like particles floating around in space. Now, the density of this is incredibly low. The average density is like 1 atom per cubic centimeter. And just to be clear, the air in this room has about 10 to the 19 atoms per cubic centimeter. We cannot achieve vacuums this good on Earth. And even the densest things like nebulas like this are much less dense than anything you'd experience on Earth. But they're a lot more dense than the surrounding area, and they're really big, which is why we can see them. So the interstellar medium consists of gas and dust. Gas is atoms and small molecules, mostly hydrogen and helium. The dust is more like soot or smoke, very small particles. They're larger clumps of particles, but they're tiny. But dust will absorb light and redden any light that goes through. So here we can see a dust cloud that is blocking all the stars behind it. And if you look around the edges, you can see that as you get closer to the edges, the stars are redder. They go from more white to more yellow. And that's because the dust scatters shorter wavelengths more than longer wavelengths. So near the edge of this dust cloud, you can see the reddening and dimming of stars. And this is a problem if you're trying to measure temperature of stars just by color, because this will distort your readings. So you need to do spectroscopic studies. Now there's also interstellar gas. This can appear in a variety of ways. If it's hot and exciting, you get H2 or ionized hydrogen regions. Here's a nice H2 region glowing. They're easy to see because they're excited and glow. They get excited by nearby hot stars and emit. They're only visible near hot stars. The UV light from the stars ionizes the hydrogen. And other elements would be seen as well. And this is only a very small portion of the interstellar gas. There are also neutral hydrogen clouds. These don't emit visible light, but they can be seen when the light from a star passes through the clouds. Additionally, there is a radio emission that you can see from gas clouds, hydrogen gas clouds. And that's very helpful. Especially when we're looking at hydrogen out in between galaxies or things like that. So cool hydrogen will emit radiation at 21 centimeters. So this is a spin flip transition. So if you have an interstellar dust cloud or a gas cloud and a star behind it, you'll see narrow absorption lines for the cloud and broader absorption lines from the star. And what happens in a hydrogen atom is that it turns out hydrogen atoms, the nucleus of a hydrogen atom, the proton has a magnetic field, a spin, and so does the electron. And they can either be lined up or opposed. And if they switch from lined up to opposed, it will gain or lose a tiny bit of energy, which when they switch, so if it goes from opposed, and so if it goes from lined up to opposed, it will emit a tiny bit of energy, and you will get that radio wave at 21 centimeters. By studying the flipping of spins like this, when we do it with nucleuses, with the actual nuclei and how they interact with each other, that's called nuclear magnetic resonance. If you've heard of an MRI, we use that to image inside your body. They got rid of the nuclear because it sounds scary. But yes, if you've ever heard of an MRI should be called the nuclear magnetic resonance imaging. So you can also have ultra hot interstellar gas, temperatures in millions of degrees. This is leftover material from supernova explosions that has been thrown out into space. And lastly, there are molecular clouds. So molecules get broken apart by UV light if there isn't anything to protect them. But in molecular clouds, there's enough gas and dust to block the UV light, leading to complex molecules forming. So this is the ultra hot interstellar gas. These are some molecular clouds. They're kind of hard to see because they're dim. Molecular clouds tend to be darker because they're full of gas and dust. But molecular clouds are also important because they're also the densest clouds. So they're the ones most likely to pass over that limit to collapse and form stars. So molecular clouds are where stars tend to be born. So here are some interesting interstellar molecules you see in molecular clouds, things like ammonia, formaldehyde, acetylene, acetic acid, ethyl alcohol, ethylene glycol, and benzene. Very musically, there's at least one molecular cloud out there that has a lot of ethanol and some other carbon atoms that we actually use as artificial fruit flavors. So it tastes like a fruity cocktail at some level. Now, interstellar dust doesn't emit visible light, but it does block light. And it's colder, so it will emit infrared light. And it can reflect the light from nearby stars. So this is an interstellar dust cloud blocking light. You can see it reddens the stars around the edges because it blocks and scatters light. It will emit infrared light because it has some temperature. But you also get what are called reflection nebulae. This is a reflection nebulae where bright nearby stars are basically lighting up the clouds of dust. And the light is reflecting off of them. So interstellar dust can reflect light from nearby stars, and you get a reflection nebula. So you see dark dust clouds over here, and over here they're lit up by these bright blue stars. Dust is very good at scattering light. Shorter wavelengths, blue, are more easily scattered than longer wavelengths. This is why the sky is blue and sunsets are red. Like this fact, the shorter wavelengths are more easily scattered than longer wavelengths. More or less is why the sky is blue and sunsets are red. Because when you look at the sky, you're seeing light scattered. So you're not seeing direct light from the sun, because that would be looking at the sun. But you're seeing light being scattered off the sky, and so you see blue more. And longer wavelengths are passed through dust. So at sunset, when you're looking towards the sun, and that light is passing through more of the atmosphere, you see the reds, the red colors coming through. So dust will redden the line of stars passing through dust. IR and radio waves better penetrate dust, allowing us to see inside of the dust cloud. This is very useful if that dust cloud is where new stars are being formed, because we want to watch the process of star formation and understand it. So here, this is a dust cloud. We can't see through it easily. But here, with infrared or radio waves, we can see through the dust cloud and see what's going on. So dust clouds will preferably scatter blue light. The spectral lines don't shift though. So if we can still identify properties of stars from the spectrums, because theirs don't change. So some of the consequences of interstellar dust. Starlight passing through dust will make the stars appear fainter than they would, so they appear further away because they absorb light, they get dimmer. And they appear redder than they are due to the scattering of light, so they look cooler. Both of these effects increase when more dust is present. There are ways to correct for this, but yeah, it is something that needs to be taken into account. So an interstellar dust grain has a small core that is either rich in carbon, like soot, or rich in silicon, like sand. Basically, it's carbony or rocky. And then in molecular clouds, they're cold enough that you get these smaller molecules, like methane, ammonia, water, condensing around these dust particles, forming little lumps of ice around the core of dust. And the typical size is about 10 to 100 nanometers, which is like tiny. This is much smaller than household dust. 10 to 100 nanometers is, this is like only a few thousand atoms across. So atoms are on the scale of about a tenth of a nanometer. The interstellar medium is divided into two parts, gas and dust. Gas can be seen visibly as H2 regions or in radio waves with the 21 centimeter emission. And dust can block the light from stars, making them appear fainter and redder than they would normally appear. Now, there's continual changes in the material in the interstellar medium. Nebulae change significantly over millions of years. Material can go through many different stages during the lifetime of the galaxy. So what was once part of a molecular cloud could form into a star and be ejected in a supernova explosion. this stuff is all moving around and mixing and changing. And this cycle gets repeated over and over again with each new generation of stars forming from material that's gone through various stages. And you can't get planets and us without a few generations of stars having happened to generate the heavier elements that make us up. So, the cycle of gas is that stars form from cool gas and dust in space. This condenses to form stars and planets. Stars will convert light elements to heavier elements through nuclear fusion. So hydrogen into helium, helium into carbon, etc. This peaks at iron. Now there are a few elements that get skipped over in this process. You'll notice it goes from helium to carbon. It skips a few elements there. And then it actually goes every other element, generally. So there's more even elements than odd elements out in the universe. And then this enriched material gets ejected back out into the galaxy. Some of the material will form the next generation of stars. This gets ejected outward by the death of stars, or just by the fact that stars spew out solar wind, but so this comes from supernovas, from really big stars, planetary nebulae, from more medium-sized, from more medium-sized stars, and just the stellar winds that all stars generate. All stars are constantly flinging out material. And each generation of stars will become more enriched in metals, elements heavier than helium. But part of why certain elements are harder to make than others, and then there's like more steps in the process to their formation. So certain elements require supernovas, and some even require additional stages beyond that. So there's sort of this process of stellar recycling. You start with a cloud of gas dust, it forms an open cluster with protostars. Those protostars can either be like brown dwarfs, low mass stars, or massive stars. The massive stars or low mass stars will go through their lifespans, become red giants or red supergiants, and then die, throwing off, the red giants will throw off a planetary nebula, which feeds back into the clouds. The red supergiants will go through a supernova, and the supernova remnant feeds back into the molecular clouds. And then their dead cores will be white dwarfs, neutron stars, and black holes. And there's a few other things that can happen. You can have a binary white dwarf in type A supernova, where it just blows up, and that feeds back in as well. So material is constantly being expelled into space by dying stars. And the earliest stars were made of only hydrogen and helium, and later stars formed with enriched material that allowed the formation of Earth-like planets and life and us. So water is actually pretty common. Where did the Earth's water come from? Well, it could have formed in interstellar dust grains. We see that the water could have formed elsewhere and then become incorporated in the gas cloud that eventually formed the solar system. Some of this material would have formed the Earth, and the water would have been released from the rocky material. It could have also, so it could have come from the Earth itself being released, or it could have also come from asteroids or comets. This could have formed further out in the solar system where more water was present, and then impacted the Earth early in its history, bringing the water. Or it could be a mix of the two. We don't fully know at this point. We live in what's called the local bubble. Turns out the region around the sun and a couple of nearby stars is hotter than usual. So if we look at X-ray emission from the galaxy, we see bubbles of hot gas, which have a much lower density than the general interstellar medium. So this is probably something that happened during the formation of various stars. and it cleared out the area of cooler gas. This is possibly from supernova or strong stellar winds. Something happened and caused these areas to clear out. The gas got heated up and blown away. And we're in the middle of one of these. This is what's known as the local bulb. And so the sun is in the middle of one of these bubbles of gas. For the interstellar medium, it's constantly changing over time of millions of years. Material in space is constantly being recycled with new generations of stars being formed from the remains of previous generations. And bubbles of hot gas exist in the galaxy, possibly created by supernova or very strong stellar winds from young, bright stars. We don't fully know. So let's start talking about the formation of stars. Main sequence layers like the sun produce energy via nuclear fusion. They convert hydrogen into helium. The sun, for example, converts 600 million tons of hydrogen to helium every second. Consumes an enormous quantity of these. Now, stars will come in a range of masses from 0.08 to 100 solar masses. Small mass stars are a lot more common, and massive main sequence stars are the hottest and the brightest. And low mass main sequence stars are the coolest and the faintest. And a galaxy like the Milky Way has enough gas and dust to make billions of stars. So star formation, the birth of stars, is sort of a constant, ongoing process. We can see it. The actual spiral arms of our galaxy are caused by waves of star formation passing through the disk of the galaxy. So here is a short video about the process of the birth of stars. So stars are born from clouds of gas and dust that collapse under their own gravity.
Welcome to an overview of star birth. In this video, we'll introduce a few of the key learning objectives for this topic. In particular, we'll explain why stars form in clouds of interstellar gas that are particularly cold and dense, explain how the interiors of newly forming stars become hot enough for nuclear fusion, and identify degeneracy pressure as the reason why there is a lower limit on the mass of a star. Our ancestors imagined the stars as fixed and permanent, but today we know that stars go through life cycles in which they are born, live, and die. Here, we see an infrared image of a star-forming cloud known as the Eagle Nebula. The spectacular cloud patterns arise from the way the nebular gas is shaped and heated by the light of young stars and stars still in the process of formation. Sometime in the future, after much of the gas is blown away by stellar winds, the cloud will have given birth to a cluster of young stars like this one. Like all the material in the interstellar medium, by which we mean matter found in the space between stars, star-forming clouds are made mostly of hydrogen and helium gas. However, these clouds look dark in visible light photos because they also contain tiny solid grains of interstellar dust that block the light of stars behind the cloud. These clouds also tend to be quite cold and dense compared to other interstellar material, and this is critical to the gravitational contraction that allows them to form stars. Indeed, the process of star formation marks the beginning of a battle between gas pressure and gravity that continues throughout a star's life. Recall that the sun always stays stable in size because of what we call gravitational equilibrium, in which the inward pull of gravity is balanced by the outward push of gas pressure. Star-forming clouds lack this equilibrium because their low temperatures mean low pressure, while their high densities mean relatively strong gravity. Gravity can therefore cause parts of these clouds to contract and form stars.
So, the Orion molecular cloud is an example of a star-forming region near us. It's one of the nearest star-forming regions. It's only 1,500 light years away. And only small parts of it are visible. Much of it is dusty. So if you'd like to see it, it's in Orion. It can be viewed with a reasonable telescope. There's a number of nice nebulas in Orion that are very pretty. Though getting good images of nebulas, you do need to get away from light pollution, which is tricky. And it is formed over a period of time. So if we look at Orion, the constellation, the stars in the belt are about 5 million years old. The stars in the sword of Orion, so the belt here are about 5 million years old. Stars in the sword are less than 1 million years old. And the trapezium stars, which are up here, I think, the Orion Nebula, are only 300,000 years old. And there's over 2,000 stars in this region. So here are some of the images of the nebula. So you can see clouds of gas and dust with young stars in them. Here's an image that's a little easier to see. You can see these bright young stars. These are these same stars. This is an IR cutting through. So this is also an image of a different nebula. This is the center, near the central section of the Milky Way. This shows several nebulae. These dark areas are clouds. These are nebulae. There are areas of star formation. And it's where stars are born. If you're looking along the Milky Way, you see a lot of these because you're looking along the disk of the galaxy. And these nebulae are very large and low density, and their size means their masses are large despite the low density. So, these nebulae are still millions of times, actually billions of times less dense than the air we have. Remember, air is like 10 to the 19 particles per square centimeter. And these are in particles, these are a million, these are like 80 or 90. Yeah, these would be about, so it would be about 10 to the 9. So air would be about 10 to the 19 for these densities here. These are similar units to that particle per square centimeter, doing some conversion. But here are some nebulas. A lot of these are going to be from the was it the Mercator series? I can't even remember the exact name. You'll see a bunch of nearby fuzzy things that are labeled M something, because one of the first surveys identifying fuzzy objects was done by, I don't think it wasn't Mercator, it was I was an Italian or something, but they're labeled M. So a bunch of the interesting nearby objects are M something. So M8 is about 1,200 parsecs away. Its average diameter is 14 parsecs. It has a density of 8 particles per cubic centimeter. Its mass is 2,600 solar masses, and its temperature is 7,500 Kelvin. M16. So these are, that's huge because it's really big, but it's not very dense. So the density of these is at 120 particles per cubic centimeter. And their masses are quite big. They're hundreds to thousands of times the mass of the sun, but they're not very dense because they're huge. Because these things are, parsecs across, light years across in size. So nebula is a general term used for fuzzy objects in the sky. It means cloud, so we use cloud to describe them. Dark nebula are dust clouds, so you see these dark lanes in the dark areas, those are dark nebulae. Emission nebulae glow to the hot stars. These are the emission, that's the red portion here is the emission nebulae. And reflection nebulae is where light from an embedded star bounces off the cloud particles. This is a reflection nebula here. So reflection is blue, the emission is red. I think this is actually a true color image. A lot of the images of nebula you see are false color images, but they're still often gorgeous. It's just that they put in artificial colors to spread the things out. So emission nebula generally glow red. This is the H alpha line of hydrogen. And the dust lanes visible in that previous figure are part of the nebula and are not due to intervening clouds. They're just denser, dusky portions. So how a nebula works? A dusty cloud can reflect blue light or scatter blue light, and you'll see a reflection nebulae. The dust lane can block light. A dark, intervening cloud can block light, and you'll see a dark area. And hot stars can excite a cloud of gas and ionize it and be re-emitted as visible light, and that's an emission nebula. There's a strong interaction between the nebula and the stars within it. So here we can see these fuzzy areas near these pillars. These are the pillars of creation, I believe. The fuzzy areas around the edges, these are due to photoevaporation, where the stars are causing the nebula to break apart and evaporate. So here is a short video continuing on about starbirth.
We've already discussed the fact that stars go through life cycles in which they are born, live, and die. But how do we know this? Like most of our current understanding of the universe, the answer lies in a combination of observations and theoretical modeling. In this video, we'll briefly explore how we learn about starbirth. The first step is to determine where stars are born. Recall that we can determine the age of a star cluster from its main sequence turnoff point on an HR diagram. For example, the main sequence turnoff point for the Pleiades is quite high, indicating that most of its main sequence stars are still living, and therefore that it must be relatively young. In contrast, the low turnoff point for this globular cluster tells us that only its very long-lived main sequence stars still survive, which means it must be quite old. The gas visible around the young stars of the Pleiades hint that they formed from a cloud of gas. The even younger cluster that we opened with provides further evidence for this idea. In fact, very young star clusters are always associated with dark clouds of gas and dust, telling us that these clouds are the birthplaces of stars. This next star-forming cloud illustrates the observing challenge posed by these stellar nurseries. Notice that some of the gas glows from the heat and light of nearby young stars, but other regions are too dense and dark to see through with visible light. However, we can use spectroscopy to learn about these clouds. Like the galaxy as a whole, star-forming clouds are made mostly of hydrogen and helium, with heavier elements making up only about 2% of their mass. Moreover, much of the hydrogen in the densest and darkest clouds, like the one shown here, is in the form of hydrogen molecules, which is why we call them molecular clouds. Many other molecules are also present, telling us that these clouds are quite cold, since higher temperatures would break the molecules apart. The darkness of these clouds is due primarily to tiny, solid grains of interstellar dust like this one, which strongly absorb visible light. But as you can see in this infrared image of the same region, infrared light can penetrate through the dust, allowing us to see stars lying behind the cloud. Here, we see a famous star-forming cloud in the Eagle Nebula. The dark pillars in this visible light photo have been sculpted into these shapes by ultraviolet light from nearby hot young stars. However, when we observe the same region with infrared light, the pillars become almost transparent, and embedded within them, we can see new stars that are just now being born. Before we continue, try answering this question. We've seen that the molecular clouds in which stars are born are quite cold and dense compared to most interstellar material. Based on what you've learned in earlier chapters, why does it make sense for star-forming clouds to be cold and dense? Is it because these conditions create more contrast with hot stars? Because they allow the cloud to glow in the infrared? Because they help gravity overcome gas pressure? or because young stars need cold and dense gas to absorb their heat? The answer is C. These conditions help gravity overcome gas pressure, as you'll recognize from your study of the Sun. Recall that the Sun is in what we call gravitational equilibrium, meaning that the inward pull of gravity is balanced by the outward push of gas pressure. The same type of balance can occur in interstellar clouds, which means gravity can make a cloud collapse only when it is stronger than the gas pressure. Dense gas clouds tend to mean stronger gravity, while cold gas tends to mean weaker pressure, so cold and dense clouds are more prone to gravitational collapse. This brings us to the idea of modeling star birth, in which we use the laws of physics to predict what should happen in a cold, dense molecular cloud. These frames from a computer simulation begin with a roughly spherical molecular cloud in which the material is spread out fairly evenly. The red color is arbitrary, since a cold cloud of gas would appear dark with visible light. Random motions within the cloud can cause some regions to become lumpy, giving gravity an edge. This leads to the middle frame, in which the simulation shows that some regions of the cloud have become significantly more dense than others. The third frame shows the cloud a little later, when stars are beginning to form in each of the bright yellow lumps. Simulations like these show that molecular clouds should indeed give birth to clusters of young stars, just as we see in observations like those we've shown in this video. Nevertheless, we still have much to learn. For example, while models can reproduce general features of star birth, they cannot yet predict exactly how much of the gas in a molecular cloud will turn into stars, or the observed ratio of high-mass stars to low-mass stars. Astronomers hope that new observations from telescopes like the Atacama Large Millimeter Array, shown here, and the James Webb Space Telescope will provide the data needed to build more sophisticated models that will uncover remaining secrets of star birth.
So, once stars are born in a nebula, they start undergoing fusion, and then they start pumping out light and stellar winds, and they'll start to actually clear out the nebula. So, strong stellar winds from young stars will clear away a good portion of the nebula, and the most massive stars don't live very long. So, they then violently explode in supernovas, and that will also clear out nebula. And both of these processes push material from around newborn stars away. But that often pushes them towards nearby clouds of gas and dust and compresses those clouds of gas and dust, which can start a new sequence of star formation. And this process can actually lead to like a wave of star formation passing along. And at the large scale structure of the galaxy, we can actually see this happen. There's sort of a wave of star formation traveling around the galaxy. Yes.
How long is this path?
What?
How long is the nebula?
It varies, but I would say millions of years. Because it depends on the specific conditions of the stars that form and things like that. But tens of millions of years, because there are still, we still see star clusters in nebulas that are tens of millions of years old. So you need to have some supernovas happen and things to fully clear it. Yeah, I'm not super sure on it. So emission nebula are made of hot, thin gas, and you're going to see distinct emission lines in them. Because the gas in them is excited by generally nearby bright stars, they will emit, and they generally glow red because they're dominated by the red hydrogen lines. And let's go over the process of formation for a star that's similar to the sun. So star formation happens when part of a dust cloud gets dense enough to collapse under its own gravity. Now, the clearing of the area around a star after it's born doesn't take that long, but the whole nebula going away, that's more complicated. And as it collapses, the center becomes hotter and hotter until eventually it gets hot enough for nuclear fusion to start in the core. So if you look at just a few atoms, gravitational force is nowhere near strong enough to overcome the random thermal motion of atoms. You need a lot. So gravity can create stars only if it can overcome the force of thermal pressure in a cloud. Because the cloud is temperature, everything is moving around pretty quickly. Gravity has to overcome that thermal movement. So gravity within a contracting gas cloud becomes stronger as the gas becomes denser. Because as gravity is stronger, the closer things are together. So as everything gets closer together, the gravity gets stronger. But a contracting gas cloud also heats up. Luckily, the gravity becomes stronger faster than the heating up does. So a typical molecular cloud has a temperature of around 30 Kelvin, so 30 degrees Celsius above absolute zero. And it's got a density of something like 300 particles per cubic centimeter. And it needs to contain at least a few hundred solar masses for gravity to overcome thermal pressure at this with this temperature and density. And the cloud can prevent a pressure buildup. So as it collapses, it's going to heat up, but it can get rid of some of that energy by converting it into infrared and radio photons, infrared and radio light that escape the cloud, and that cools the cloud down. So it does heat up, but it's a big cloud, so it can emit some of that heat as light. So here's sort of the stages in the formation of a star. You start as an interstellar cloud. That cloud starts to collapse, and it fragments. So the relevant unit is then a cloud fragment. Then as the cloud continues to collapse and the central temperature gets hotter, and the size gets smaller, and these are time in years for things, you get a protostar. So a protostar is something that looks like a star, but it hasn't started fusion yet. So it's dense, it's hot, it's glowing, but fusion hasn't begun. And then eventually, the core of the star will reach 10 million degrees Kelvin, and fusion will begin, and you'll have a star. And then over the next little while, it will move on to be a main sequence star. So if we want to look at the process of stellar birth, well, direct observations are impossible because of all the dust. Because stars form in clouds of gas and dust, the clouds of gas and dust get in the way. So we can't look with visible light. But we can use infrared or radio waves. So this process starts with the initial collapse. This is a short time, in thousands of years. There's the formation of a dense core within a clump of gas and dust. The gravitational force grows and becomes dominant, and a rapid collapse begins. And as this clump collapses, so this is some fragment of the cloud, it becomes easier for material to fall in at the poles than at the equator, because this lump of gas and dust was probably spinning a little bit, and as it contracts, it spins faster because of conservation of angular momentum. If you've ever seen like an ice skater doing a jump and they pull their arms in to spin faster, or a diver doing a flip and they tuck to spin faster, that's conservation of angular momentum. Same thing happens when a large body collapses. Any rotation it has will increase. So you start with a big cloud, it starts to contract, triggered by something like maybe a shock wave from a nearby supernova, a pressure wave from a nearby star. And as it contracts, bits will get denser than other bits, and this cloud will fragment into smaller pieces. Each of these smaller pieces can become a star. So this simulation begins with a turbulent cloud of gas containing about 50 solar masses of gas. And you can see as random motions in the cloud cause it to become lumpy. And the denser areas are going to collapse faster than the less dense areas and draw things towards them because of gravity. So any increase in density is going to get concentrated. So it becomes lumpy and it will separate into several pieces to form into denser lumps. So here you can see separating into several pieces, and certain stars are forming in each lump. So it forms many small lumps of matter, and each lump can go on to form one or more stars. So each lump of a cloud in which gravity can overcome pressure can go on to become a star, and a large cloud can make a whole cluster of stars. So stars get born in groups, in clusters, because they started as a big cloud that broke into lumps. And as stars begin to form, the dust grains that absorb visible light will heat up and then re-emit infrared light. So invisible light is in this image, the star forming regions still appear dark, but in infrared, they are brightly lit up. So visible light can't penetrate, but infrared light can. So we can see through the dust in infrared light. And in some regions, it's lit up by star formation. The long wavelength infrared light is brightest for the regions where many stars are currently forming, as you can see here. So the second stage of star formation is where individual cloud fragments begin to collapse. And once the density is high enough, there's no further fragmentation. Once you got a dense enough lump, it's not going to break into any more pieces. It's just going to collapse on itself. At stage 3, the interior of the fragment has started to heat up from all the gravitational potential energy from the collapse, all the friction from the collapse, and because it's being compressed by gravity, it warms up and it reaches about 10,000 degrees Kelvin. So here we can see the Orion Nebula, which is thought to contain interstellar clouds in the process of condensing, as well as protostars. So here are interstellar clouds that are currently, we think, condensing, and here are some protostars. So once you get this hot ball of gas, this is a protostar. So the core of the cloud becomes a protostar, and it makes its first appearance on the HR diagram. It's now bright enough to be seen. It's cool, the outer layers are cold, but it's still a big cloud because it's collapsing inwards. So it's reasonably bright. And it's going to continue to collapse and get hotter and hotter in the core. So this is a T Tauri star hidden within the solar mass stars. Once that protostar collapses and gets hot enough, you'll also get strong stellar winds, which will clear out the remaining cloud of dust around your protostar. And you can get jets of material along the axis of the polar axis. This is called a Herbig-Haro object, where a jet of material strikes the interstellar medium. You see this sort of arc-shaped structure. So as you have the protostar with an accretion disk, which could become like planets, you get jets of material off the poles, and where it hits other material, you get this Herbig-Haro object. It's like a shock wave. And here's an actual picture of one of these. So we have a protostar here, and these are the Herbig-Haro objects of jets of material hitting their surrounding medium. So then at this point, planetary formation has begun, but the protostar is still not yet in equilibrium. It hasn't reached balance. All of its heating is still coming from gravitational collapse. So it's bright, looks like a star, but it hasn't quite begun fusion. So it's emitting jets of material, it's forming planets, but it hasn't quite started fusion. It gets hotter and denser and more active. It's cleared out most of the general dust around us. Well, it's going to push, if you like teleported a star into a nebula, it will push nebular material out away from it with stellar winds out to some distance where it dominates. But it's not going to be as strong as a very young star, which is emitting a lot more material as it's achieving balance. But it will clear an area around itself. And then the last stages can be followed on the HR diagram. It gets hotter and denser, so it gets smaller, so it actually gets dimmer. And then at this point, the 6 here, this is when fusion begins. So this is just gravitational collapse heating it up. And then fusion begins, it warms up, and then settles into equilibrium on the main sequence. So the protostar's luminosity decreases even as its temperature rises because it's getting a lot smaller. And then eventually the core will reach 10 million degrees Kelvin. Nuclear fusion will begin. The protostar will become a star. And then shortly afterwards, that star will reach a stable state. So once it becomes the star, the core starts emitting a lot more energy. The outer layers will expand a little because everything is going to heat up. The whole star is going to get hotter. It will move up and then settle onto the main sequence, where it will sit for something like the sun, something like 10 billion years. So the star reaches the main sequence and will remain there as long as it has hydrogen fused in its core. So here are again those jets of material that are emitted as material condenses onto a protostar. Here's a couple of protostars in Orion. And I think I will stop there and we will start with this video next time. Yeah, so that is it for today. Let me just check who's here. Okay. So if you haven't signed in, remember to sign in. I'm going to stop sharing and